Okay, hi, welcome back. So we're just continuing the session. In the previous sessions, we have seen ISRO previous year questions, induction machines. Okay, now we're continuing the same session. Okay, I hope you're all ready. Give it a thumbs up. Give it a thumbs up if you're ready. We'll move to the first question. So you can check these, these previous year questions are not only just helpful for answering written test or clearing written test. They are very much important to crack interviews also. They are important to build the knowledge as well. So you're actually learning you're understanding the concept or recapping the concepts with the help of these lovely questions. Okay, so let's get to the first question of today's session. Yes, hi Praveen, hi. Are you trying or not? Just try, simple thing. It is said rotor oscillations. Don't just look at it. Try, read it. Let me explain. I think you're trying. Try those who are trying. Let me explain this. Simple question. Okay. Uh, what is given? It is given. The voltmeter is giving 120 oscillations per minute. And where that voltmeter is connected? That voltmeter is connected to the rotor of an induction motor. Means it must be a slip ring induction motor. That's why you have access to the rotor terminals. So if the voltage is of 120, I mean, the voltage is having a frequency of 120 oscillations per minute, then per second, how much will be there? Per second, how many oscillations? 120 by 60. So this is 2 oscillations per second, means 2 cycles per second, means 2 hertz frequency. Rotor frequency is 2 hertz. That's what he's trying to give. This entire line is trying to say rotor frequency is 2 hertz. That's it. Okay. And then when the stator frequency is 50 hertz, what is a slip? Stator frequency is, rotor frequency is equal to slip into Fs. Fs is given as 50, Fr you got it as 2. Slip, simply find out slip. Just do the math, you'll get option C. Okay. I'm going to the next question. Hurry up. Ashrit is saying B. Okay, let me explain this one also. I'm explaining this one as well. A 6-pole, 3-phase alternator running at 1000 rpm. So when it is running at 1000 rpm, 6-pole machine, what is the synchronous speed? Synchronous speed, I mean the rotating speed is 1000. So corresponding frequency is how much? Frequency, if you just do the math, you will get it as 50 hertz frequency. Okay, 50 hertz frequency it is generating, the alternator is generating 50 hertz. And it is supplied to 8-pole induction motor, means its corresponding ns, if you calculate for 50 hertz, it will be 750 rpm. Okay, now rotor frequency Fr is equal to 2 hertz. Then what is the speed of operation? Definitely not this, because synchronous speed itself is 750. Rotor speed is not even 750. It will be less than 750. Without even doing anything, you got this as 720. Answer is D. Okay, just an idea. Of course, if you want to calculate, you can calculate nr is equal to ns into 1 minus s. From this you can find out s value, then you can find out this, but you don't have to. The concept, from the concept I can say answer is D, because a synchronous machine, the induction motor will always turn or rotate at less than synchronous speed. Yeah. Next question. This is also a straightforward question. Come on, don't take too much of time for these silly questions. Okay. I mean, these simple questions. So what can be done? They are simple. So a rotor resistance is given like this. So I'm considering this rotor resistance, what is given is referred to the stator. That's what R2 prime. And the resistance corresponding to mechanical output, that is, yes, referred to again stator side, R2 prime into 1 minus 1 by s minus 1. This is what the resistance, which is equivalent to the mechanical output. So answer is A. Yes, Raju, Ashrit, you're absolutely right. Okay, so answer is yes. Straight questions, guys. For these questions also, if you're taking much time, then it's funny thing. I mean, this is also a simple question. This is also 15-second question. 15 seconds, I think, yeah. Quick. I think 15 seconds, more than 15 seconds ago. So let me answer this. Induction motor air gap motor operating at slip S. The ratio of gross power to the air gap power. Gross power to the air gap power. This is gross power is power mechanical. PG is, don't think PG is a gross power. Air gap power is PG. Okay. So 1 minus S by 1. We have a powerful relation. From that relation, I'm writing this. You know the relation, right? Direct equation. So this ratio is, yeah, answer is B. Yes. Praveen, you're right. Ashwit, you're right. Raju, you're not right. Okay. Next question. Okay. Let's see who is going to answer this one. You got the answer already. See, somebody's saying, let's check it out. Just for the sake of time, I'm quickly wrapping. Let's see this. Let's see this. Interesting point here, guys. Interesting point. Understand the question here. Because this is one of the popular questions again. Okay. So you should know how to answer this. A three-phase induction machine draws 100 kVA at a power factor of, this is, interesting question. Analytical question. Interviews also, you can get this question. Induction machine we have that is drawing 1000 kVA at a power factor of 0.866 lagging. Now what we are doing is we are connecting a synchronous condenser in parallel to this. Synchronous condenser is connected and that is having a load of 750 kVA and 0.707 leading power factor. Okay. Now with the combination, this combination has how much? This white color boxed one, this combination is having how much power factor? Okay, total the power factor of the total load, this total power factor you want. Okay, so let's see that. First of all, power factor is what? Power factor formula, can somebody tell me what is the power factor formula? Power factor is, don't say power factor is cos phi. Power factor is, it's actually P by S. P by S is a power factor. Okay, factor of two powers. I already discussed about these details. Okay. First of all, tell me what is the active power for this, what is the reactive power for this. Okay, find out these two for this particular load. Let me just use the same color. Okay, so for this you'll have to find what is P, what is Q, and here also you have to find out what is P, what is Q for this load independently. Okay, P for this particular value of load, I have the values, I'm giving it. Okay, 866 kilowatt. Here this is 500 kVAR. Now for this P value is 530.25. Here 530.25. Here also 530.25 kVAR. This is kW. Okay. Now see. This is lagging, this is leading. Okay. And the net reactive power, let's talk about net reactive power. Q is equal to 500. If this is minus, this will be plus, because lagging is minus, leading is plus 530.25. If you take reverse, it will be reverse. If this is plus, this is minus. So which value is higher? Leading reactive power is high or lagging reactive power is high? Tell me in the comment quickly. Leading reactive power is high or lagging reactive power is high? Leading reactive power is high, it's clear, 530, right? So leading reactive power is high. So the total load is of leading nature, not lagging nature. Not lagging, it is leading nature. And that leading is not so huge. That leading, I'm not doing math. If you do math, you will get the answer definitely. Okay, because total active power, sum of these two, and total reactive power, so you can find out total cos phi, total power factor. But intuitively, I'm trying to answer. So both are wrong. Leading, and that leading also just only 30 kVAR compared to the huge active power. So that leading will be close to 1 unity power factor. So I would say answer is B. If you just go by math, you can do it. Okay, just go by math. Find out tan phi. Tan phi is equal to total reactive power by total active power. From there you can find out phi. From there you can find out cos phi. You will be getting 0.99. Okay. Okay, guys. Good, Ashrit. I think, yeah, if it is 860 kilowatt, okay, 860. Maybe I would have some calculation mistake or something. Yeah, if it is so, good. Let's move to the next question. I think you could see I'm quickly wrapping the questions because we have a power failure. I think there is a damage nearby. So there is a blast of transformer or something. So AC is not there, and it's too suffocating. This complete projection setup, the lights and all. That's why I'm quickly wrapping. Let me explain this as well. See, question is looking a little bigger, but if you do the solution, it will be easier, not so difficult. Yeah. A three-phase, four-pole, 400 volts, 10 kW slip ring induction motor has a rotor resistance and stator resistance and rotor resistance are given. Okay. The voltage across the slip rings, slip rings voltage is given, per phase value is given as this 141. Interesting. The motor develops this much torque at this particular slip. Okay. And the rotor current is 6 ampere. Okay. What is the rotor current if, not if, rotor current of, it should be off, rotor current of a voltage, if a voltage is inducted to a rotor. Okay, so it is said if you are injecting something into the rotor, okay, EMF injection method you are doing, and by that method you are having slip from 0.08 to 0.02. So slip is reduced means what? Speed has increased. Okay, speed has increased. Now with that rotor injection method, under this slip, what is the rotor current? Okay, it's a straightforward question because it is said it is developing a torque of this, and when you are applying rotor injection method also, it is having the same torque. Torque is same. That's what the statement. So we know torque is proportional to I2 square into R2 by S. You know this formula? Basic thing. Okay. If it is a three phase, it will be into 3. Okay, it's all right. So from this, I can say for the same torque, I2 square by S must be same because rotor resistance is same. Means in the first case, whatever the rotor current square by S, that ratio should be equal to the second case. This is, let me take it as B, this is A, this is B. Okay. Now you have everything in this. You have everything in this. You have this I2A is given. How much is that? Rotor current is 6 ampere and this is unknown. This slip is given as 0.08. This slip is 0.02. Just do the math, you'll get answer as D. Okay. This is the main relation. Main relation, just focus on that, then things will work, fall in place automatically. I hope you got it. I hope you got it. Shall I move to the next question? Large question in competitive exam. See, large question when you are getting in competitive exam means answer will be easier. You have to have a good practice of those large questions. Okay, conceptual questions. They are maybe lengthy in reading, but if you read line by line carefully, answer will be easier. Okay, because they know it's not a gate exam, right? If it is a gate exam, it's obviously tough there because its time is that the proper time is given to you. But ISRO kind of exams, they are giving limited time, so they will frame the question accordingly. Okay, you don't have to worry on that. So practice is a key thing. In normal exams, if you are getting a big question, means you need to be happy because solution will be easier. Okay. I think this is an easy question because we already said in one of our discussions also, double case induction motor, squirrel case induction motor, normal case induction motor really has having poor starting performance because you cannot add extra resistance into the rotor bars, unlike your slip ring. That problem is overcome using this double case induction motor, high starting torques, or sometimes deep bar rotors. Yes, we can use similar things for this. Okay. Next question. Okay. I think let me answer this. Maybe let's see how many of you know this. Then I quickly go. Yeah, we got answer. People are saying, let's see who is right. Okay, I think you're guessing maybe. I think you started guessing. So to stop your guess, let me unveil the answer. Loading capability diagram. Loading capability diagram is drawn for alternators, synchronous generators. So what is this loading capability curves or generated capability curves you can call? It will set the limits. It will give the boundary of operating conditions, like you will do in case of SCRs, SCR operating zone, MOSFET or power MOSFET, power BJT operating zone. Similarly, this generator capability curve also, it will set the operating region. Okay, just Google it, you will get some basic idea about it. I'm moving to the next question. Yep. Good. I think everybody answered correctly rather, because it's a straight question. We discussed this question a lot of times also in our discussion itself. A three-phase slip ring induction motor, the electrical rotor losses are proportional to, yes, electrical rotor losses means what? Electrical rotor losses means copper losses. Copper losses, yes, they're trying to say copper losses. They just said in a different way, that's it. Okay. Copper losses are proportional to slip. Powerful relation, powerful relation. This relation, if you keep, then things will fall in place. Most of the things in case of induction machine. Okay. Yes, Venugopal Reddy, you're absolutely right. Yes, Ashrit, you're right too. Next question. Nice. See, theoretical questions. These are theoretical questions which you can easily answer. Uh, the blocked rotor test. The blocked rotor test. We have the answers, my guys. Block rotor test of a squirrel cage induction motor means it's just like a short circuit test of a transformer. Okay. In case of short circuit test, we're going to find the series branch parameters. Open circuit test, shunt branch parameters will be finding. You know that. So series branch parameters is series resistance and series reactance and refer to stator. That's also important. You should not just miss that. Okay. It is referred to the stator. So that's it. And we have a question by Sampath. Sir, every circuit has a written path, but where in delta connection? Okay. See, for you to understand that specific question, because three-phase circuit, in three-phase circuit, you normally encounter this problem. If it is a star connection, let's take it a star connection with no neutral. That's also possible connection, star connection with no neutral. So where is a neutral path? Likewise, delta, where is the neutral path, return path? So to understand this, you have to know the beauty of three-phase. Why we are going for three-phase connection, you have to have that understanding. Okay. And with this question, I recommend, again, I'm just popping that question here. With this question, to understand this question, every one of you should watch our Y series questions. Okay. Why three-phase is one of our popular three-phase series questions. You watch that, you will get not only answer to this specific thing, but to lot of other things, you'll get a clarity. Okay. Sampath, just do that. And yeah, maybe in the next session, you tell me whether you understood the answer or not. Yes, Venugopal Reddy, he's trying to give something. Okay. Anyways. So with this, I'm wrapping up this question. I mean, this session is over. It's a very quick session. Okay. It's nice participation from all of you. So what we'll be winding up this. We're not going to the winner wheel this time because of this hot condition over here for me. So okay, thanks for joining. Have a good time. Bye bye. ठीक है भाई खत्म कर दो. Bye guys.